in this presentation is about the technical, let us say, requirements and what is mentioned in the grid course, particularly for the wind and the hybrid power plants. And a little bit about just Suzlon in brief. I will not take much time about that, and how, let's say, the renewable energy growth is happening all around the world. And then I will come to, let's say, two very interesting concepts that's introduced: the round-the-clock hybrid park and also the wind solar hybrid park. Basically, in India, because I see at the moment, particularly on the hybrid park, this is the one of the, let's say, the largest market that we see in the world. And then I will give you, let's say, the high-level overview of the grid codes all around the world. So Suzlon is, let's say, was founded in 1995. So it's already 25 years old company based in let's say, the headquarters in India. And so far we have, let's say, commissioned more than 12,000 turbines, more than 1,800 customers, and total, let's say, installation base is 18.8 gigawatt. We also did some, let's say, solar projects, but not doing any more in India. It's not so, let's say, we are not so competitive. So it's a commercial region, not the technical region to do the solar project in India. And then, let's say, we have our technology centers, basically in Germany, in two locations, Hamburg and Rostock, and also in the Hanglo, where we have the blade developments center. And then in India, we have in Pune, Baroda, Chennai, let's say, the technical supports and design supports. And Denmark, we have our development team sitting in Aarhus and working mainly on the SCADA. So we have, let's say, the international organization, international teams working on different aspects of our wind turbine designs and wind farm designs. And yeah, so that's I just took from the, let's say, the IEA, the growth, how it's happening. I think most of you know about the renewable energy growth worldwide. And on year basis, you see there is something 10 to 15% growth happening. And in some of the countries, now depending upon their, let us say, the need, basically energy independence, their own security, not depending on other countries, and also the growth that's happening in the individual countries. So demand is increasing. So they want to have a more and more the renewable energy. In India, let's say, they target by 2030 to have 450 gigawatt of renewable energy installed. And we know also, let's say, in the Europe and other countries, some of countries are targeting 100% renewable energies by 2050. How realistic it would be, that we will see, but at least the growth shows that it's a really good growth happening in the renewable energy area in, let's say, in most of the countries. And India is one of the countries which is also leading now. So I have taken, let us say, a lot information and the examples from India on the hybrid parts and also the technical parts, but I also cover some other countries. So here you see there are, in the last 2 years, we have seen number of, let's say, the projects coming up in India, basically wind, solar, hybrid parks, and there is also, let's say, the requirements. If you want to install the storage, you can do this, but it's not mandatory. And we see, at least in the coming years, in the next 3 to 5 years, there would be more than 25,000 megawatts of projects of the hybrid, and mostly the project that we will see coming up in India would be hybrid. That's why it's very important to talk about the hybrid plants and what are the requirements. Of course, I am not going to talk about the operations and other issues. I think some of the speakers have spoken about that, but mostly on the technical part, the grid connectivity parts and the regulation, what is required to, let's say, design such a systems and connect to the grid. So the one of the, let's say, here you see in the last day, one of the big project, that's a 5,000 megawatt project, which is still open and under the bidding process, where the India came out with a new concept. They call it a round-the-clock power from the renewable energy. And basically the renewable energy are not so good, let's say, predictable, and so they cannot provide, let's say, like the power from the thermal plants or the gas plants 24 hours by 365 days. But still, this concept, when they are saying the round the clock from the renewable energy, that I will explain to you later. What do they mean by this? And this is the first project still in the bidding process. So in general, you see this is a very typical grid connected, let us say the large scale hybrid park configuration, where you see here on the where I have mentioned the pooling substation, and behind these pooling substations is the main transformer, which is depending upon the grid. That's in India, it's a 220 kilovolt to 33 kilovolts, and the integration of the different components of the hybrid park, like solar, like the wind or the storage, happens at 33 kV, because this is what we, let's say, studied and found out this is more economical, and also technically, let us say, provides us the good solutions and the flexibilities. And then every park, let's say, have its own controllers, and then there is sitting on top of this is a master controller that we call as a hybrid park controller, which is, let's say, then interfacing to the utilities, the SCADA system, to the weather stations, and taking the inputs from the markets and operators, and decides which part of the park to be controlled in what way. I also see in one of the presentations from the Ireland and others, they were talking about the operations of the different parks and different, let's say, the requirements they are considering, their technical functions. Yeah. And so in, at least in the utility scale, grid connected systems, that is the configuration that we found is the best configuration techno-commercially. So like I said, the round the clock power concept, no, that's from the government of India. What they say that, okay, in order to address the issue of intermittency, limited hours of supply, and low capacity utilizations of the solar or the wind, they said, okay, you can bundle your renewable energy plant with the conventional plants. That means from the thermal plants, or it could be gas plants, but they want to have a 24 hours supply. The power which is committed, if I say it's my 100 megawatt, and then you should be able to supply 100 megawatt on 24-hour basis. And this is just a configuration as example of the round the clock project. Now here you can see that there's a wind component, there's a solar component, and depending upon the requirements, when you calculate whether how much storage is required or not required, but you have to fulfill the technical requirements, you can add the storage. But the condition here is that in this case, you have to charge the storage or the batteries, whatever it is, from the renewable sources. You are not allowed to charge the storage from the conventional plants. And then let's say you can complement this with the thermal plant. So I have given an example. For example, if you have a 500 megawatt project here, the capacity can be much higher than this, but you cannot, let's say, inject more than 500 megawatt into the grid. So for a 500 megawatt projects or the grid connections, you can have, let's say, the combination of 1000 megawatt. Here you see I have given just an example of 100 megawatt wind, 300 megawatt solar, 200 megawatt of thermal. Just as an example, it's a 600 megawatt installed capacity. But you can increase it, no problem, depending upon, because you have to fulfill 100% availability, then you can size accordingly. Of course, then you have to do the techno-commercial evaluation, what makes sense or what doesn't make sense. So these plants can be co-located. That means it could be, let's say, in the same states, in the same districts, or could be in the different locations. And the capacity can be higher. So that means if it's a 500 megawatt, you can have a factor of 2 or factor of 3. We did some, let's say, the simulations and studies in Suzlon, and we think in order to meet such a requirements, the overload capacity would be around something 300%, not less, that you can fulfill minimum requirement. And then what you have to guarantee in such a plant is the minimum annual availability of 85%. If below this you go, then there is a huge penalty, which I will show you in the next slide. And also, it has to provide the power during peak hours, the guaranteed power during peak hours. So you know that, okay, at the moment, the conventional plants are providing you the peak powers, but the same is expected from these plants. And this has to be also guaranteed. If you fail to meet these requirements, again, there is a penalty. The another technical requirement from the plant is that 51% of annual energy out of this whole plant has to come from the renewable energy plant. And then they define, let's say, the peak hours every day. There is a 4 hours where you have to supply the peak power that you will define, let us say, or that you will put in your bidding contract that, okay, how much power during the peak hours you can supply, and then you have to meet these requirements. So this is a concept. In some case, let's say, when we know that, okay, renewable energy growth is happening and they are displacing the conventional plants, but at the same time, you cannot, let's say, take out all the thermal plants or the gas plants from the grid. And the growth of renewable energy will make, let's say, these plants economically unviable. So in my opinion, from the policy point of view, they are trying to, let us say, save the thermal plants and the conventional plants by complementing with the renewable energy plants. So by that time, let's say the life is over, renewable energy can take over, but before that, at least both can survive. So that's the more on the policy level. What we did also, let's say, the one study to find out, let's say, how the hybrid plants or the wind or solar can, let us say, help in meeting the peak power demand. So here you see, this is a typical, let us say, one day, July to September, 3 months, let's say, the demand curve in India, at India level, a very typical characteristic here you see the demand is in the evening, and sometimes it's also in the morning. So the peak demand in the morning and in the evening. So if we go with the renewable energy plant, that's why you see on the left top, on a particular day, the productions from the conventional plant, from the solar, from the wind. And as we know that solar is only during the day times. In the evening, there is no solar. So if you only use the solar plant, you cannot meet, let's say, the number one, the peak demand, and also you cannot fulfill the 100% availability requirement. So you have to combine it. And what we see from the previous slide is, let's say, from this generation, the wind generation. So that can really help in meeting the peak power demand. And we also see the pricing, because if you go for the peak power supply, and then of course you have to make a big investments, and if there is no return on the investment, nobody will, let's say, install this. But the pricing, what we see today from the hybrid plants, what is being bid in India is just 1/3 of the price that you get for the peak price. So there is an incentive in order to install, let's say, the hybrid plants, and also to do this service of the peak power. That is one, just an example from this 5,000 megawatt round the clock, how the calculation is done for the availability basis. So let's say divide the time blocks in a month's time in 60 hours, and then you see that, okay, my renewable plant is of 200, total of 500 megawatts, where I have a renewable energy capacity of 250, thermal is 200, and then total is 450 megawatts. So during 60 hours, I am only telling the utility that I have a 450 megawatt. That means 90%. That's why you see the availability is 90%. Only when you have all the three components available at their full capacity, then you are 100%. And if you don't, let's say, meet these requirements, there is a huge penalty. So that is a big challenge, not for the industry, and I think also for researchers, that how do we meet this requirement while keeping, let's say, cost and the performance at the acceptable level. So here you see the penalty, because the big penalty, if you make a wrong assessment in the beginning of your project, let's say, design, and then you find out, oh, my availability is falling less than 85% or not meeting 100%, that you can see the penalty is something like 4 times than what you will get out of the energy that you sell to the utilities. This is a big, let us say, the penalty. I have seen this first time in India in this particular project, nowhere else. Then there is also a penalty going for the availability down 85% and also during the peak hours. The second configuration is the wind and solar. It's here in this case, this is a little bit relaxed as compared to the round-the-clock supply. Here you have the same configuration, that means the wind plus solar and the storage. And here the condition is that if you are installing 100 megawatt solar, then 33 megawatt has to be wind. That's the minimum conditions that has to be fulfilled in order the project to be qualified as a hybrid project. So either you can have a 100% wind and then 33% solar. And again, as an example, the contracted capacity, the capacity of the project like 500 megawatt you can inject, but you can oversize your plants here in order to meet, let's say, certain technical requirements, availability here. The minimum annual, let's say, the utilization factor of the plant has to be 30%, but this has to be declared in the beginning. So you make the calculations, you make the estimates, you select the best sites. Sometimes it's quite challenging to find the right, let us say, sites where you have both wind and solar. And yeah, there are a lot of uncertainty. So this project has to run for 25 years. So the challenge is to make the assessment of the wind and solar resources 25 years in advance and fulfill these conditions. The storage is allowed, let us say, if you think that, okay, the variability is larger and that can bring some benefit to you, but then you have to see your costing of the projects, whether that makes sense or not. So far, let us say there have been 2 projects in India where they talk about the size of the wind and solar, let us say something like 2.7 times the rated projects. That means for a 500 megawatt project, there would be installation of 1,300 megawatt wind and solar, plus storage separately. We don't know at the moment from, let us say, industry point of view, whether this would be a good solutions in long run or not. But yes, there is a project and we will see when it comes to life. Then there is also the technical, let us say, the configurations, what you can do and what you cannot do here. So you have the possibility of these 2 configurations where you can have a small wind component, solar components, then you can bring them to a substations, and from substation you have to only carry 1 line to the grid substations. It is not possible that you can directly put your solar or wind project and connect to the grid substations. And this is the way where you can save, let us say, some cost. And I saw in one of the presentation today also, they were talking about the savings when you are, let's say, utilizing the existing infrastructure or the common infrastructure for both the components. And we also see this advantage, but this is not so big, honestly speaking, when we try to utilize the infrastructure, the grid infrastructure, yeah. But that depends upon project to project and site to site. In case of, let's say, the hybrid project, now the penalty in case of round-the-clock project was 400%, but here, let us say, the penalty is quite low. That means it's just 50% of the payment that you get. So if you don't fulfill some of the conditions like cumulative utilization factor or the availability, and then, okay, you will be charged little less, 50% of your tariff. But still, there would be a penalty, and this penalty could be used if you make, let's say, the wrong assessment or the wrong forecastings, because there is a requirements of the forecast 1 day ahead, and this is also very critical. Then I come to a little bit on the grid codes. If you have any questions on the round the clock on the hybrid, please you can ask me and stop, no problem. Hello.
Hello. We have tended to keep questions to the end.
Okay.
If we might be simpler.
I'm okay, Nas, but even if in between, I'm fine. Okay. So here you see what I did is made a, let's say, overall overview of the grid code. So what we learned out of this when we doing this exercise of the grid code as a let's say the wind turbine design company, I have to design a turbine, and that should meet the technical requirements of the grid codes in various countries where we want to focus it. And the biggest problem or the biggest challenge for us is that the grid codes keep on changing very frequently. And every country has their own requirements. So you see there are more than 230 grid codes at the moment. There are something in the draft stage, there are something published, and sometimes like in a big country like USA, you have so many utilities, and every utilities have their own requirements. So very comprehensive analysis of each and every parameters of the grid codes has to be done when we start designing our new product or the new turbine, for example. And the grid code that what we find basically, they are not, let's say, depending upon the technology. It's technology neutral. So whether you use like in wind turbines, it's a DFIG turbines, or it's a full converter turbines, or it's simply a direct connected turbines, or the solar inverters, whether you use different kind of inverters, or it doesn't matter. The regulations and the technical requirements are common. And one, let's say the particular that I have noted in some cases, in some countries, there are some requirements which is applicable at turbine level and some are applicable at park level, the point of common coupling. This makes it more complex situations. But this is understood by us that okay, every country has their own systems, own way of operating the systems, and needs, like I showed you in the load demands and the reactive power compensation into the systems, and some reserves, that all decides what they need. But as a turbine designer, when I have to start designing the new turbines, I have to consider all these requirements so that I need not to design every turbine according to the countries. But that makes our life a little bit miserable, because then it becomes quite expensive in some cases. And customization, if we do, then it's a long development time, and then we make a compromise that what is the best to do in this case, and which country we should focus, for example. So whether it's the IC standards or the IEEE standard, I also see IC standards sometimes is a bit slow. Like I saw you may be knowing the IEEE standard for the harmonics, IEEE 519. I think first it was published something like in 1995 or something, and then the second revision came in 2014. After 15 years, the new revision came. But the grid codes are in that way is quite fast. I take an example of South Africa. Every year they are changing the requirements and ask us to keep our plants compliant with the upcoming grid codes. So this is a big challenge. And even if I am installing today turbines, I don't know what will be the requirements after 2 years. So we have to also forecast, let's say, do the research that what kind of requirement may come that we should consider only today. So at high level, let us say the most, let's say, critical requirement that we see in all the grid codes is the low voltage ride through. Only thing is the magnitude varies, the duration varies. That's why you see here in the curve, some grid codes requires, okay, the voltage dip, let's say up to 0% residual voltage. Some says 15%, some say 20%. The duration could be 150 millisecond to 1 second. But in some of the cases, so what you can do is the turbines, for example, you design turbine or the inverters. we are talking about the park. We are talking about not about the individual turbines, but there is no such facilities available as on today that we can test the whole park. If it's 100 megawatt or 500 megawatt or even 25 megawatt, we just carry out the measurement at the turbine. That's at 690 volts or at the most at 33,000 volts, but not at park level. So in order to prove the compliance, because this is very critical, let's say for the grid security point of view, stability point of view, if there is a fault and the turbine should not trip. But this also puts a lot of, let's say, the stress on the turbine components, particularly electrical and so the mechanical components into the systems, and also increases the cost. Sometimes the requirements are not clearly, let's say, spelled out, and that makes it's difficult to prove that yes, your park is compliant, your turbine is compliant, because if you go to the certification agencies or you go to the grid authorities, they have their different interpretations. So the requirement, what is the common, whether it's a wind park, solar park, or it's a storage supporting the wind parks, or it's a hybrid park. So for me, for example, when I start designing my turbine, I will consider all this and say, okay, my turbine should withstand up to 1 second, should dip up to 0, and like this. So this is a big, let's say, the LVRT right through capability we built, but that, as I said, also increases the cost of our developments. And then here you see what is expected during the fault. Sometimes they say, okay, every country, they have a different requirements of the response time, the magnitude of the reactive current that has to be injected during the faults. But at the park level, as I said, it's quite challenging to prove this. And sometimes many grid code, they said, okay, let us wait when the real fault happens, how your park will respond, and then we will see the compliance, whether you are compliant or not compliant. I give you an example of the South Australia in 2016. Highly unpredictable. Nobody thought that such a situation will come. Yeah, on the 28th September 2016, there was a very, let's say, it was very windy. The wind was something like 120 kilometer per second or something, hours, the speed, and lightning was happening. And most of the wind farms, let's say one after another, start tripping because the LVRT events here you see on the top left side, there was 6 LVRT events of very small duration of something 120 millisecond to 200 milliseconds, up to 50% to 30% dip. And 6 such events happened in less than 2 minutes time. And what happened with such an repetitive LVRT event, because this was never thought that such situation will come. We always think of, okay, one LVRT event comes, then it is over. And then maybe next comes after some months or hours or so like this, but not in such a 2 minutes time. And this led to, let's say, the tripping of wind farms. Some wind farms could, let us say, withstand 2 or 3 or 5, but nobody had programmed, let us say, the turbine to withstand 6 or more in less than 2 minutes time, because it's a highly unstable grid. And then there was a blackout. South Australia went into the blackout, and the question started coming because grid authority challenged us that say, hey, why your turbine tripped? We said, you did not say to us that we have to withstand 5 times or 10 times or 20 times in such a short durations. How can we plan it? That's what I was saying. We have to plan and think of such a situations while designing the turbines or the inverters for such applications. And this could be really lead to a disaster in some cases. And to test, let us say, such situations, maybe some of you might have seen this. What I am showing you on the picture is the big containers. This is LVRT laboratories. That's a mobile laboratory that we take to the site, connect to 33,000 volts, and really short circuit the 33,000 site voltages to test, let us say, the wind turbine capability to meet the different requirements of the different grid codes. So it's a, let's say, the big campaign that we have to do. The only, let's say, difficulty here is that we can only do such tests when there is a wind, sufficient wind, rated winds we need. We need a low wind, medium wind, high wind to conduct, and then we have to wait for the wind, right wind to be there to conduct the test. So sometimes it takes months to complete the test campaign. Then the second requirement that I see is the critical one is the high voltage ride through. Although this happens very, very rare, let's say I haven't seen so many such cases as compared to the LVRT, but still there is a very high requirements of the high voltage ride through, where they say, okay, at the point of connection, the voltage can go as high as 140% of your rated voltage. Still, your turbine should remain connected. In some cases, it should also absorb the reactive power in order to bring down the voltage. But if you see the durations, which is 130% or 140%, 2 seconds, 3 seconds, sometimes it's quite difficult to get even the components, that electrical components, to withstand such a high voltage for such a duration. So you have to have a customized design of the electrical component which is not available off the shelf. And again, to conduct such a test, so until, let's say, a year or 2 years before, there was no such containers available even for conducting the test. Now we see, at least in the last years, so many grid codes like in Germany and others, they say now you have to prove, you have to test it. So some test laboratories have come up, and we are able to conduct the tests. One can also do something simulations, let's say in the laboratories. You may be knowing some of the good laboratories, they have some test setups. They can simulate, let's say, such grid faults and test, but this is not the complete turbine. This is only, you can do, let's say, the combinations, nacelle and converter or generator, let's say, combination, but not the whole turbine. It's quite difficult to, let's say, simulate such a situations in the laboratories. That is, again, let's say, the different requirements in the different countries for the reactive power during the high voltage sites here. The one of the, let's say, the another requirement, that's the reactive power. Although it's a known, but the reactive power requirements, if you see at the park level, it's quite different if we go from one country to another countries. Although this requirement, reactive power requirement, can be met by the wind turbines and some additional equipment, the problem is with every change there is huge investment cost here at the park level. So if somebody is saying, okay, I have to meet the South Africa and then I move to, let's say, NSOE, here you can see the square, the reactive power from 0% to 100%, you have to fulfill the requirements. It's a huge requirements and control complexities in the plants. When we are talking about, let's say, synchronizing with the grid and controlling the turbines and additional statcoms, capacitor banks, inductor banks, it's like a big substation that one has to install and then coordinate along with the grid and all control functions. So it's a complex system that has to be properly, let's say, coordinated. Only then you can achieve the required performance here. The another one is the grid frequency regulation. I think some of the previous speakers also talk about the frequency regulations, and the renewable energies like wind, solar, and or combinations can provide you some of the supports for the frequency regulations. But again, there is a huge variations in the requirements from country to countries. Some countries says, okay, you can only do the over frequency response. That means if frequency goes high rated, you just reduce your power by certain percentage or by during certain times. But some countries say, yeah, you have to put a reserve and then with the reserve, then you regulate the frequency. But putting a reserve, that means you really need a very good forecast that what is the power available, what you are producing, how to prove that, okay, I have kept this reserve in reality in the park, because the utility of someone has to pay for that. So this is quite still, let's say, a technical challenge for us to prove what I have and what I can offer, because this is not all the time that you need it. There was also some discussions on the synthetic inertia. So I think Professor Damian was also explaining, or there were some questions on the synthetic inertia of the fast frequency response there in the previous presentation. So it is also not very clear. Sometimes, let's say the grid code, like in Canada, they first came out with the synthetic inertia, and I also see in the IC standard they are saying something. Some grid codes say the fast frequency response. There is not a uniform definition that one can understand. So if you move from one country to another country, requirements, it seems like it's the same, but sometimes it's different. But wind turbines still can provide this, let's say, the feature, the synthetic inertia, by slowing down the rotor, and the response time is not a problem. If we see the measurement of the frequency that we do, it is possible that we can measure the change in frequency and the rock in 20 to 40 milliseconds time. But the question is, how reliable is that? Because sometimes in the grid disturbances, small grid disturbances, the frequency cannot be read or calculated or measured very reliably. So sometimes you will respond to the false, let us say, events. So that is a big challenge, and that's why one has to do at least 4, 5, or 6, let's say, the cycle sampling and averaging, so that you take a 20 millisecond measured values, take 5 values, wait for 100 millisecond or 200 milliseconds, do the averaging, and then you make a decision. Yes, it's a real frequency event, low frequency event, and then your turbine respond to that or your park respond to that. But simply, let's say, taking one value and responding, then it would be a nuisance. This is our experience, at least, doing this feature development, during feature development. But in some countries, when they are saying that, yeah, we need to have such a frequency response, because this is also putting in stress or stressing the wind turbine components, and one has to maybe oversize it, or maybe have to provide more, let's say, maintenance to the turbines, because in some of the cases, like in the countries, I see 30%. In Australia, I think they're talking about 60 to 70% of the time you have to provide the frequency regulations. In some other countries, it varies. So 60-70% of the time you are, let us say, just changing, accelerating, decelerating your rotor. That is where I say it's stress your mechanical systems and increase the maintenance cost. Although electrically it's quite simple, easy and fast as compared to the traditional, let's say, generators, but still it has its own, let's say, disadvantage. In the solar, because they don't have such a rotating mass, and cannot provide what I have seen, let's say, in some cases, using the large capacitor banks or some small storage or some virtual inertia they try to create in order to fulfill these requirements in the solar plants. But at least in the hybrid plant, when we talk about, so you have a wind, you have a solar, and also the storage, then you can make a good choice, and the combinations, either it could be, let's say, based on the pre-decided, that under what conditions which source to use. But that's quite helpful when you have these three components together to meet such a, let's say, stringent requirement of frequency regulation or synthetic inertia. So the one question that I ask myself, or I ask you, can we make a common technical requirements or the grid code worldwide? So then it's easy for everyone to follow it, design, and have a, let's say, the benchmarking of all the products. But our experience says that would never be possible, because each country has their different power generation mix, its load characteristics, and there are other specific circumstances. For example, in some cases, like in Australia, you have a long transmission lines where the system makes it vulnerable to faults. In India also we see it's although it's now only the one grid, but still from south to north, it's a 5,000 kilometer distance, and something happening in south, how it is impacting the north on the west, it's very specific to the countries. And what we also see is the countries, that's our also experience, they simply adopt the requirements of the grid codes from the more advanced countries or the experienced countries like Denmark. No, they were the leading one developing the technical requirements. And I have seen many countries simply copy those requirements without understanding whether they really need that or not. But that will not change. That's what it will continue to happen. So what exactly is expected when I speak, let's say from the utility point of view, what they are expecting, because they have been operating, let's say the conventional plant, thermal plants, gas plants, and they see that okay, the renewable energy plants should also provide the same services, similar services or better services than the conventional plants. So that's why the plant that we have, the renewable plant we have to provide all that kind of features, even the more advanced features, like we talk about synthetic inertia, fast frequency regulations, and other regulations. Even the black start, for example, is now under discussions. I see a lot of research happening in the universities and also in the IC committees working on this, have to come out with a clear requirement how this has to be fulfilled, and feature has to be developed. But this is clear expectations from the utilities before they can, let's say, 100% adopt the renewable energies. And it's not their fault, because for them it is important that their grid remains secure, reliable, and stable, and can provide quality power supply, because that is also their commitment, that they have to provide a quality supply to their customers. And this can only happen when the renewable energy plants is able to meet same kind of forecasting, reliable, let us say, the supply, like you saw the concept round the clock supply, which is nothing but it's the moving in this direction, in the conventional plant directions. And what I see the trend today, so there are some trends which is going to become, let's say, the mandatory technical requirements. Sometimes we are talking like, yeah, we will do this and this, and we also track the trends, what's happening, but we also see that becoming very soon as a mandatory technical requirements and being put into the connectivity standards. And the big challenge is if you let us say are not able to design your system, whether it's your park system or it's a turbine or this, and compliant with the grid code and prove it, then it is restricting your entry into the market. If I have designed a turbine, let us say, considering only Indian requirements, and you want to sell in Germany, it will not happen. So you have to fulfill, let us say, the technical requirements of the grid codes, prove it by experiment, by measurement, by simulations, so many methods you have to use to prove it. In some cases, if let's say you don't consider some of the requirements, the grid authorities in some countries I have seen, they can simply ask you to disconnect your park from the grid or drastically reduce your generation. So for example, when I'm talking the reactive power, okay, you were asked to provide 100 MVR, let's say the reactive power compensation for a park, and 10 MVR is not available or 20 MVR is not available, 10 or 20% is faulty, then the grid authority says, because it makes my system, let's say, risky, and it could be a problem, and then you have to reduce your generation. So just keep your generation level according to your reactive power supply. And today's time, like we talk about the inverters or the converters, and the IGBTs, all the electronics, their reliability is not 100%. All across the industry, I would say it's 15% failures you can expect. So the inverter converter that we are using today, it's a 15% fail all across the industry. And that also puts, let's say, a lot of challenge for us how to make these converters even 100% reliable, or at least 99.99% reliable. So this is just an example from Indian, let's say, technical connectivity standards from the grid, which they have published very recently, just 2 years before, and came into effect in the October to August 2019. So what this is, the ramp rate. No? So at the park level, your park should not, let's say, exceed plus minus 10% change in power per minute. And this is sometimes, if you read this statement, it's not clear under what conditions we have to fulfill this requirement. Yeah, the ramp rate has to be plus minus 10%. What happens? It's a solar plant. All of a sudden, cloud is coming, and then you see a sudden drop in the power happens. Wind, of course, in that way is quite stable, but solar is, that can happen. So one has to really use very advanced technology like we are developing and working on a sky camera based, let's say, this cloud monitoring systems where we can predict it in advance and already start, let's say, taking action rather than this sudden jump happens and we are non-compliant or cause issue in the grid. Then on the second side, you see on my right side is the frequency response, where they talk about a 10%, let's say, the response within 1 second. So in case of, let's say, the solar, it could be fast because there is no moving parts, and it can, let's say, provide you the power in less than 1 second. But in case of wind, if you have to accelerate or decelerate your such a huge mass of the rotor, it's quite challenge to increase 10% power in 1 second. So that means it's a very, very large, let's say, ramp rate required here. Then we also see the capacity. So from 10% to 100%. Okay, operating the wind turbines at 100%, and then you want to say that, okay, please increase 10% more. It's like in the conventional plant where you have already have a reserve of 10%, and that reserve you use to meet this frequency regulation requirement. But in case of the wind or the solar, we are always operating at the maximum generation point according to the wind. We don't have a reserve. So there you try to use, let us say, this synthetic inertia or the rotor energy to fulfill this. But again, there is a question comes here, what is the duration? So they don't specify the duration for how long I should provide you this response. And that's what I said, this kind of missing information in grid codes leads to a lot of complexity for the design people. Then I have added at the end, let us say, some of the references on which, let's say, basis I prepared these presentations, and yeah, so some of these tenders and the grid codes, we studied all about that, and you see just an example here. This is for the tenders that is published in India. So frequently they make changes. So very, very frequently, even for one project in just 6 months' time, 10 times they are making changes, and then it also changes the concept. You have to be alert on for these changes to keep in your mind and the design the system accordingly. Yeah, so with this, then I conclude my presentation. Thank you for your patience, and I know you will have some questions, and I would be happy to answer if there are some questions.
Thank you, Pukhraj. Very, very interesting. I'm sort of wondering, in terms of the grid codes, I mean, you talked about your 230 grid codes that you had been looking at or monitor. Do you see things improving in the future? Do you see grid codes converging towards common requirements, or do you see them diverging?
Yeah, that's how I see this. Now, so depending upon the individual countries, because they have a different requirements, different power mix. So I don't see it's converging. In Europe, at least they try to do this, and so no? And so
Yes.
let's say the common framework they say, but still the countries, individual country have the right to make changes, make it more stringent. That's the minimum requirements.
And I mean, do you think there's partly here an education role for system operators in term or those people that sort of define the grid codes? I mean, you sort of implied that in some systems they just copy
Yeah.
something from other systems. So is there a need to actually, I suppose, educate system operators in terms of, we can do what you want, but be fair?
Yes, that's exactly my point. At least it is very, very important that the people in the utilities, people in the policy makings, they have to be educated and they have to be told whether that's really useful or not useful.
Yes. Okay. I can see Heng Wu has their hand up.
Yes, thanks for the presentation. I have a quick question. You have mentioned that it is not possible to perform the fault rise root test at the plant level. Can you elaborate more why it is? Because I can see in HVDC industry, people are already perform the fault rise root test in the transmission system level.
Yeah, because when you are talking, let's say, about the fault, no, so you have a, let's say, normal the grid connection is depending upon the countries, 220 kilovolts or 132 kilovolts, and you have a 100 megawatts or 500 megawatt of plant. That means you have to create a short circuit at that time, and then you have to have a short circuit capacity of at least minimum 5 to 10 times, because the plant will create such a high short circuit currents, and such a equipment does not exist. You cannot create a intentionally the short circuit at a transmission level. This will collapse all your grid.
Okay. Thanks.
Okay. I was also wondering, I mean, you mentioned the diversity of grid codes. So how do you tackle that? Do you have maybe sort of a small number of base designs that you sort of say, yes, that one can work in that country and the other one can work in another country, or how much variation does it create for you?
Yeah, that's what I said. It's a quite big challenge for us. Now, so first of all, at least in the new product development, so what we do in the company that we decide, okay, which country we will go with the new product. Okay. And when we decide in the beginning, okay, that is our country of focus, then we go into this investigations. Okay, what are the grid codes today and what can come in the coming years? No, because the product which we are today designing, at least it take minimum 2 to 3 years. And after 2 to 3 years, it has to be in the market at least again for 3 to 4 years. Now, say otherwise it would be totally out of market. And so we have to make a forecast at least 5 to 7 years in advance today. And that's why we interact with the universities, the researchers, and our own, let's say, contact in the policy making. So it's like a scouting. We have to do it.
Okay. And Kaushik.
Yeah. Thank you, Dr. Pukhraj, for a very nice presentation, and thank you for agreeing to present here. I was wondering, there is this lifelong debate on whether this requirement should be put on grid codes and as mandatory, or they should be on based on market, and you are provided revenue for provision of some of the services. Do you see in especially in the developing countries where the grid code is being developed from very primitive version, that this discussion keeps on coming, or this is just this is not there? People just prefer, the system operators just prefer to have it in the grid code as requirements.
Oh, this is the grid codes are mandatory requirements, and there is no way. and this has to be fulfilled. I can give you one example, like in South Australia, when the blackout happened, they had a backup system. So when the generation went out, let us say because of the LVRTs, they had a standby generator to support. And the generator is only, let us say, designed and kept in standby to fulfill these requirements. Unfortunately, at that time, the generator also didn't work. So just you keeping it running just for it, let's say in the idle conditions, and when the time came, it also tripped, failed. So sometimes you have a backup system that doesn't work, but now there were, I think, 2 hours or 3 hours of blackout in South Australia. You can imagine the loss, and now who will pay for that loss? It's a big problem. So that's why for the utilities, it's important they make a very stringent grid codes. They learn from the other countries and simply adopt that. They don't want to take any risk, although they don't have a technical capability in some cases. And so it's easy for them to copy it. I have seen this I have to tell this, but in some countries, simply copying it, and when we ask them, okay, can you please explain why do you need it? They are not able to explain why do they need.
Okay, thank you for explanation.
Okay, so thank you. Thanks for the presentation and for answering the questions. So as I say, it was very interesting.